So this brings us to this whole idea of why did I teach you all these formulas for energy, like force times distance, et cetera, right? And then that is that we can solve conservation of energy problems. So this is the crux of it, right? Conservation of energy says that the total energy of a closed system will remain constant. Now closed means that energy can't go in or out of it, yeah? Okay, so this is not really a closed system. If I get it swinging and we come back in a year, for sure it's not going to be swinging, yeah? If we even come back in 10 minutes, I think we would notice that it's swinging a lot less, okay? But if we could neglect air friction or something like that, look at this over a short period of time, okay? Guys, hello? Okay, if we can look at this over a short period of time, its total energy is going to be constant, okay? So let me just give you a for example, okay? Let's say, for example, I push on this thing and I give it some energy. Well, you know it's got energy now, don't you? And it doesn't have kinetic energy. It's not moving if we ignore the fact that it's going, what, 900 miles an hour that way because of the rotation of the Earth and all this stuff, right? Okay, just in our frame of reference, right? We know it's got energy. Why? What kind does it have? Potential. I've raised it up, haven't I? In moving it to the side, I've actually raised this thing up. And in fact, that would be the only way we could actually figure out the work that I did, is that we would have to calculate the MGH that it's got now, right? Because the force I exerted at first wasn't very much. It got more and more and more, and we would actually need calculus to solve for what the amount of work that I did. But we know that the work I did gave it the energy that it's got. This is, by the way, called the work energy theorem, that the work I do on it turns into the energy that it has, and in this case it's potential. Now, let's suppose I gave it 10 joules in pushing it to the side. I really don't know how much I gave it, but let's say it's 10. Okay? If I let it swing, well, at the bottom, it's going the fastest. It has no potential energy, so now it has 10 joules of kinetic. And if we look at it, let's look at it almost at the top. Let's say it's got 8 joules of potential. How much kinetic does it have? 2. You guys are good. Yeah, it's got 2 joules of kinetic, right? Let's look at it when it's almost at the bottom. It's got 1 joule of potential. How much kinetic would it have? 9. It's always going to add up to 10. So if you can find one of them, you can just by subtraction determine the other one. Yeah? Isn't that clever? So if we know the height of this thing, we will know its velocity. And the other thing that is true is that if I drop it from this height, if energy really is conserved, it should come back to that height and no higher. Okay, now it could go higher, it could go lower, right? Yeah? And if it goes higher, can we stop? Hello? Okay. If it goes higher, I might die. Okay, so let's change the topic here. Let's suppose you need to kill somebody. With a simple blow to the face, how is it that we can kill somebody? What's the death blow? What is it? There it is! Nick over there. He's a mild-mannered student by day, but he's got this secret, right? And how does it work? You know how it works. Everybody knows. What does it do? Their nose into their brain, doesn't it? Yeah, there's like these little bone spurs that are just poised on the most vital part of your brain, right? And then if somebody hits like that, the bone spurs go back into the brain and the person dies, okay? Now, I don't know if the butt of his hand would actually do that. I think this is probably partly a myth. But I'm pretty sure that a bowling ball named Artie, okay? That's the name of this bowling ball. Yes? I'm pretty sure a bowling ball named Artie would do the trick, wouldn't it? Yeah. Okay, so I'm gonna mush this thing up against those bone spurs, okay? And there's a lot of nose in front of those bone spurs, so I'm going to try to compress it into my nose. And I'm going to hold my head against the back here so that when it comes up, it's got something hard to press against, right? So if energy is not conserved, it might come up a little bit higher, right? Yeah? Yeah? Okay? And I'll die, right? And I'll just, apparently, and I'm right over the trash can, so I'll just, right? Okay? And then what you do is you just press the button there. Deb will go, yeah, what is it? And you just say, well, energy was not conserved today. Murray's dead. We need a substitute teacher. And she'll find another teacher in the building, probably McCaffrey, right? And he'll come down and he can teach the rest of the lesson, okay? Or you guys can, right? Okay? So are we ready for this? Do we talk about air friction? Right? I think we did a little bit, right? So with air friction, it might not come quite as high, right? Yeah? You know, so really I should be pretty safe, right? I'm pressing it up hard against the... Okay? All right. Did I talk about the proper way to release it? Because what you don't want to do, you definitely don't want to give it a push, right? Because then it like, whoa, it really comes up high, right? Why does it come up really high? Because it started here, but I did a force times a distance, right? Yes? And a force times a distance, when it comes back up, it comes to a higher spot, yes? Yeah, all right. Thank you. Okay, so let's solve the, what? I didn't, did I? Okay. Whew, you guys are sticklers. Okay. Are we ready? Thank you very much. Thank you, thank you, thank you. And my nose is still nosular. There we go. Yeah, it still loses energy fast, isn't it? Yeah. It's attached to a very large steel pipe. Is it? It still doesn't matter, you know, because it's, I mean, even if its arc changes, right? It's just, yeah. Here we go. Thank you very much. I'm happy to be alive. Energy was conserved. Stay. All right. Okay. Now, as much as I would love to set up a formula or a situation where we've got work, I push the bowling ball, right? Okay. And it already is above the zero elevation that it has potential energy. And even before I push it, it's moving, right? Okay. And then afterwards, some of the energy goes to frictional forces. And afterwards, it is still not it's not the same height it was, but a different height, right? And it is still moving. These problems are rare, and we must celebrate them, right? Usually these things are like one thing on this side turning into one thing on the other side, and we'll practice those. And then it might be that it has kinetic and potential, and at the end it only has potential or something like that. So these kinds of problems, you just have to read the problem and look at what it is that they say they give you, and you just read between the lines and figure out what the formula is. Okay? So let's take a look at this one. A cart moving 4.5 meters per second at the top of a 1.75 meter tall hill is going how fast at the bottom of the hill? And that's how you'd see it in English. You would draw this picture probably. Yeah? You would draw this picture to possibly help you understand this, right? And then the question is, what do we have? Do we have any force mentioned for a distance? No, not so much. At the top of the hill, do we have potential energy? Indeed we do, yes. Okay. So we've got 250 times 9.8 times 1.75. Okay. Is it moving at the top of the hill? Yeah. Yes. Can you have two different kinds of energy at once? Yeah, and you could just add them up, couldn't you? Right? Yeah, so it is moving and it is on top of the hill. So we add those together, right? Times 4.5 squared. Now we're ready for the right side of the equation. Is there any mention of a friction force that slows it down? An expenditure of energy? Not so much, really, right? Does it still have potential at the bottom of the hill?
No.
No, it doesn't, right? Is it moving at the bottom? That's the whole point. It's asking us what the velocity is at the bottom, right? So this is 1/2 250, and then we don't know the velocity, right? So there's always something we don't know. So that's what you set up. Can we divide 250 out of every term? Can we? Is that legal? I don't know if it helps you to do that. Right? So these kinds of problems, I call these roller coaster problems, the mass always cancels out. Okay? Mass both gives us more potential and more kinetic, but also requires more, so it just cancels out like that.